Okay, we're going to begin lecture 18, and that's where we're really going to get in to the final stages here. We're actually going to show an example problem as a separate part of this lecture, just as an example, but we're going to deal with the standard step method. So I'm going to go over that. I'm going to spend all my time kind of going through the equation and then going through the methodology, because we end up using a trial and error approach to computing the water surface profile, and I'll show you how that's done. So again, you're used to seeing this. This is the basically the diagram I used to show you the equation. I've got the water surface elevation upstream, water surface elevation downstream. If we're going with subcritical flow, we go from computations from downstream to upstream. If we're in supercritical, we go the opposite way. The reason we do that is that if we don't follow those directional schemes, the numerical computations start to diverge from the correct answer. We also have the velocity heads at each location, and we have the total head loss is due to both the friction and expansion contraction. And again, to remind you, counting purposes, K+1 is downstream, K is the upstream value. So this is our standard step method equation, and this is our head loss due to friction. This is the head loss due to expansion contraction. So as we mentioned, there's multiple ways to look at the friction slope, the average friction slope. This is the method that I use because that's what the USGS prefers for steady backwater modeling. You can use any of these and they're about the same. These are all options within the HEC RAS model that you're going to be learning in the lab and also doing for Project 1. So if we look at this, we look at our equation, and this is if I'd use the average conveyance method to look at friction slope or friction losses. This is the friction losses if we use the geometric mean approach. And so when we look at this, this is our equation. We're basically talking K is the upstream, K+1 is the downstream, and these are the head loss terms here. So if we look at this expansion contraction, when it all boils down to, when we look at the head loss due to the contraction, that's basically this C sub C value. That's a coefficient times the absolute value of the difference between the downstream and the upstream velocity heads. And here's the head loss due to expansion. You can see the expansion coefficient, same kind of thing. We're still using the kinetic energy upstream minus the kinetic energy downstream. What we typically do if we have a contraction is to use a value of 0, assuming that it's fairly efficient. And if, you'll be able to change this in the modeling scheme, you can always raise this value up. For expansions, we use a value of 0.5. So again, reminding you of the energy correction factor, and if you've got subdivided cross sections, let's say that you had a main channel and you had some floodplains here, this is a kind of a standard type of way to do it. You'll have section 1, 2, and 3. So I would calculate a K1 and an A1. I'll put that as a little A, K2 and a little A2, K3 and a little A3. Those would all go into the computation of the alpha for that particular cross section. This is just a slide to remind you of kind of the ins and outs of doing step backwater modeling, computing the water surface profiles. You've got to basically make sure that your cross sections are close enough together that you can pick up the details of the geometry changes. And so if I'm modeling this in a sense of a step backwater problem, and I'm just looking at the flows that are just out of bank, and I would have, looking at this as a flow that mainly was in this main channel here, that might be my cross-sectional distribution. if I had to look at this, let's say that I was at major flood, so it filled the valley wall to valley wall, I might have only a few cross sections, but they would go like that because the preponderance of the flow goes this way. Now, if I've got flow that stays in this channel and lower flows, and I'm modeling that, I'm going to select an N value that's probably totally different than the N values here, because you've got a lot more roughness elements as you pick up these surface features, and the flow actually in this main channel here becomes very negligible compared to the flow that is carried in bulk when these are very, very high flows. So anyway, just kind of a nice slide for you to look at and look and think about what you're actually modeling. So let's talk about the methodology of the standard step method. And so the first thing you're going to do is you're going to determine the state of flow. Is it subcritical or supercritical? And you're going to, from that, which way your computations are going to proceed. You can determine the normal depth, and usually what will happen with that is that may end up being your downstream starting boundary condition. For lack of no other knowledge, I mean, if you've got a section where there's a waterfall or something, you could assume critical depth there. But typically what we do in step backwater modeling, knowing nothing else, we'll take the normal depth for that particular part of the channel, and we'll go downstream far enough and survey in the cross sections where we're below our reach of interest, where we need to be accurate with a model. And you'll see when you do step backwater modeling, the errors that are associated with your assumption of whatever your starting boundary condition dissipate and attenuate as you move upstream. And so you can see from that standpoint, you get those errors attenuating. And so the assumption of normal depth is actually a fairly decent way to start most of the modeling exercises. So if you look at that point in the reach that you're starting, and that's the K+1 location, you're going to compute all the properties of the flow: the area, the hydraulic radius, the conveyance, the friction slope at that location, the energy coefficient, and then sort of the kinetic energy head. And then your next step is to go up to the K node, or the next cross section that you're going to. So let's say these are, typically modeling, maybe 500,000 feet apart. You go up to that next cross section and you make an assumption of the water surface elevation at that location. So this is an assumed value, and even the automated models will do that. And so you've got to kind of know what kind of flow conditions you're at, whether you're, and that's why we kind of spend a lot of time talking about water surface profiles. Am I an M1? Am I an M2? Am I an M3 kind of situation here? And so let's just say that you knew that it was kind of constricting, and you had a bit of a backwater effect, maybe a little beaver dam or something like that, and you might think that you're in some sort of M1 profile where it was increasing in depth. So that might inform the way you would make your assumption of the cross section upstream. You would assume that the depth's getting smaller as you're moving upstream. So once you make that assumption of that, so you've got an assumed K of the water surface elevation at K, you can compute all the parameters: the area, the hydraulic radius, the conveyance, the friction slope, and the alpha, and then the kinetic energy head. And basically at that point, you've got enough information to also calculate the average friction slope through that reach, and you've got an idea of what your value of the head loss due to expansion contraction. We'll talk more about that in a second. All right, we're going to solve then the value. We're going to go through, and actually then we've assumed a value of WK. Now we're going to go through and compute this value of WK based on knowing everything else, because again, this is what you started with, because this is the downstream side of things, and we calculate this based off of our assumed value of WK. This is actually the WK computed, and we're going to look at that computed and see if it matches the assumed. If they do not agree within acceptable tolerance, and usually that's within 1/100th of a foot, then you set that new, you repeat the process, and assume and take that WK assumed and make that what you now that becomes what you previously computed. And then you just repeat these steps 5 and 6 again until the WK computed is equal to the WK assumed. All right, so we're going to go through an example problem here, but I'm going to shut it down for this lecture and restart the recording for the example problem.